we can treat gradient as a vector, right? So we can treat it as the first one is derivative with respect to x, derivative with respect to y, and derivative with respect to z. Right? If we're talking about three-dimensional case, that's what we're going to have. Now, if we also have a vector function, for three-dimensional case, for two-dimensional, we use PQ. For three-dimensional, we're going to be using PQ and R. And when we have two vectors, we can multiply them, right? And there are two types of multiplication. There is dot multiplication and there is cross multiplication. Okay, so we can potentially take dot product and we can potentially take cross product. Okay, so those are two potentials. So when we're doing dot product, we're going to call this one, is going to be called divergence of f. So which means divergence f is going to be, if now we do dot product, so it means you take derivative of first one with respect to x, take derivative of second one with respect to y, take derivative of last one with respect to z. Okay, so that's divergence. If we take cross product, that is going to be called curl. So to calculate curl, if you're compatible with three-dimensional determinants, then we're going to be doing the following. So we're going to be doing following. So basically, we're going to calculate the following determinant. We're going to write down I, j, k, like x, y, and z. Then we're going to write down partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. That is gradient. Then we're going to write down coordinates of f, which is p, q, and r. Then we're going to calculate that determinant. So I will come with derivative with respect to y, r, derivative with respect to z, q. J, because the second one will come with minus, derivative with respect to x, e, derivative with respect to z, r, plus k, and k will be the last one, derivative with respect to x, p, derivative with respect to y, q. And then we calculate 2 by 2 determinants. So curl f is going to be I times main diagonal minus secondary diagonal. So derivative of r with respect to y. Minus derivative of q with respect to z. Minus j. Derivative of r with respect to x. Minus derivative of p with respect to z. Plus k derivative of q with respect to x minus derivative of p with respect to y. So that's the formula for curl. I'll write it the same way as the book says. I partial derivative r with respect to y minus partial derivative of q with respect to z. In the book, they brought that minus inside. So plus j. So we have partial derivative p with respect to z minus partial derivative r with respect to x plus k partial derivative q with respect to x minus partial derivative p with respect to y. That's a curl. So it's a bit ugly formula for curl. Okay, so if you try to memorize it, memorize it. Otherwise, see how it comes basically from your cross product, and it comes from a determinant. So if you're comfortable with calculating determinants, that's basically what is going on. Okay. So let's calculate. So we want to find, if we have vector function which equals to xci plus xyz j minus y squared k. We want to find curl f. Curl f and divergence f. The curl is harder to find. Divergence is straightforward. So let's do firstly divergence. So it's gradient times f. It's partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, xz, xyz minus y squared. So basically take the derivative first with respect to x, derivative second with respect to y, derivative of last one with respect to z. So we should z plus xz plus 0. So divergence f equals to z plus xz. It's gradient times f dot cross product. So it's I j k partial derivative with respect to x, partial derivative with respect to y, and our function is vector function is xz xyz negative y squared. Okay. I, and we look what's going to have y. So we're going to have derivative of y squared. So it's going to be negative 2y. Then derivative of xyz with respect to z is going to be xy. And we're going to minus. J will come with minus because it's the second one. Now derivative of y squared with respect to x is 0. Derivative of xz with respect to z is going to be x, and because it's z with respect to z, it's going to be x, right? And because it's secondary diagonal, it's minus. Because it's the third one, it comes with plus, so plus minus plus. Derivative of xyz with respect to x is going to be yz. Derivative of xz with respect to y is going to be 0. Negative 2y minus xy times I plus xj plus y z. And that's going to be curl f. So I guess a physical notation, what those means. Curl basically will indicate if there is any curl happening at a point or in the neighborhood of a point, and it will tell you around which axis that movement is happening. Okay, that's a physical interpretation of curl. So curl will tell you if there is like something happening around the point, like curl, if the fluid is moving like in the circles around the point, and if it is, then it tells you around which axis probably that rotation is happening. Okay, if there is no rotation, then curl is going to be 0. Divergence as a number, so that number will tell you, again, if you treat that vector field as a fluid, then it will tell you basically if you treat like a very small neighborhood around the point, it's like net inflow, how much fluid coming in and how much is leaving through the point. So that's kind of your net inflow. So that's what divergence. If divergence equals to 0, that means that as much fluid is leaving as coming in. Okay? So that's kind of your physical interpretation. So curl of gradient, right? So you remember a gradient of f is going to be derivative with respect to x, derivative with respect to y, derivative with respect to z, right? That's definition of gradient. Gradient of vector. So that's not divergence. There is no dot product. It's just gradient of. Okay, so let's calculate curl of it. So we're going to write down I, j, okay. Partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. Right? So I'm going to get I partial derivative with respect to x, to y, partial derivative with respect to z, fy fz minus j, partial derivative with respect to x, partial derivative with respect to x, fz plus k, partial derivative with respect to x, fx, partial derivative with respect to y, y. Okay. I. Main diagonal is going to be partial derivative of z, and then I take derivative with respect to y, minus partial derivative of y, and then I take derivative with respect to z, minus j, partial derivative of z, and then I take derivative with respect to x, minus partial derivative of x, I take derivative with respect to z, plus, and this one is going to be partial derivative with respect to y and then x, minus partial derivative with respect to x and then y. If function f of x has continuous second order derivatives, so if it has continuous second order derivatives, then it doesn't matter which way we're taking derivatives. So if f has continuous, that's kind of comment, then it doesn't matter which way we're going to take the derivative. YZ is the same as ZY. That's kind of comment. So if you go in XY or YX, you're going to meet, if function is nice enough, has continuous second order derivatives. So in this case, what is happening, that is going to be 0, that is going to be 0, that is going to be 0. So what we got is curl, so we can make it as a theorem, curl of gradient equals to 0, function has continuous second derivatives. So curl of gradient of function equals to 0. Okay, and we can now get corollary from that. So you remember our conservative field. Field is called conservative if it equals to gradient of function, right? So now if you put in this theorem and the statement of conservative together, then you see field is conservative, it's if it's gradient. If it's gradient, when you take it curl, then it equals to 0. So we have field F is conservative. If and only if curl of F equals to 0. So that's a way to check conservative. And F has continuous partial derivatives. I'm not saying second order because I'm already treating F as already the first derivative, right? So like one less. So that's how we're going to check if F is conservative or not. We know how to check it for a two-dimensional, and now we know how to check it for three-dimensional case. Right? Say we have F, which is, let's see, y squared z cube. 2x y z cube. And 3x y squared z squared. Determine if F is conservative. So essentially, we're going to be calculating curl F, right? That's the question we're actually going to be answering. If curl F equals to 0. If it equals to 0, it's conservative. If it's not, it's not conservative. Okay. I, J, K. Derivative respect to x, derivative respect to y, derivative respect to z. 2x y z cube, 3x y squared z squared. And then derivative with respect to y, I'm going to get 6xyz squared minus derivative with respect to z, 6xyz squared minus j, derivative with respect to x, 3y squared z squared, derivative with respect to z, 3y squared z squared plus k, derivative with respect to x, 2yz cubed, derivative with respect to y, 2yz cubed. So I got 0. According to my calculations, I got 0. So f is conservative. So f is conservative.